talked about like survivorship curves and stuff, didn't I? Did I do all that with you guys?
Yeah, you're all up to like the logistic
I was up to here. Okay, let's start.
Yeah.
I've lost my mind as to where I was. Okay, so here we go. Remember what we're going to do now is model population growth. I can probably go through this kind of quickly because you all did this already in lab. So I'm going to do some parts of this very fast. That's why I'm going to get caught up to a few little minutes I was lost there. In order to build this model, remember we want to look at changes in population size over time. And in order to make the model mathematically a little simpler, we're going to assume the only way we gain individuals is through birth, and the only way we lose them is through death. So we're going to ignore immigration for right now, just to make the model simpler. That's the only reason. And so if we use a capital N to represent population size, time is measured in generations. We could have a big B and big B that represent the actual numbers of births and deaths in a population. But it would be more interesting to actually have births and deaths measured in rates or per capita rates, like little b and little d. And we've sort of condensed those down into this single term r. And r you can just think of as the rate of increase. And notice that r could be 0, meaning that your population is not increasing. It could be positive, meaning it's increasing. Or it could be negative, meaning the population is decreasing. That basically your death rate is greater than your birth rate. And so r itself can change, and so that's where we thought to put r as a derivative. Basically, you talk about an instantaneous rate of increase, and then that allows you to have a model that incorporates different r values as conditions change. So is this kind of where I was, right? Where I was talking about these two basic growth models, right? An exponential growth model and a logistic growth model. So in an exponential growth model, we assume that a population is only limited by biotic potential, by its ability to crank out babies. So the rate at which you can maximum crank out babies, that's going to be the rate at which you grow. This does not incorporate any aspect of the environment, such as carrying capacity, right? The assumption in this particular growth model is that the only factor limiting growth is the rate at which you can crank out babies. So the entire equation consists of only that reproductive rate, that maximum reproductive rate. And you end up with a line like shoots straight up like that. And it doesn't even matter a whole lot if r is 1, so you're increasing 100% every generation, or if it's 0.5, you're only increasing by 50% every generation. The line still goes straight up, right? And this is a very, very rapid rate of growth, way to expand a population, or a very rapidly expanding growth model. And there are examples of natural populations that can grow exponentially, at least for short periods of time. So I showed you this elephant one. If you remove poaching, it's able to expand exponentially, at least for a brief period of time. Humans are in an exponential growth phase. So you can have exponential growth phases in natural populations. You just can't have them indefinitely, right? They can only persist for a relatively short period of time. So then that brings us to this logistic growth model, which just shows a more realistic example of what the overall growth model for a population would look like if you incorporate this term K, which represents carrying capacity. So you'll notice the first part of this equation is exactly the same as what we just had for exponential growth. But by bringing in this K value, K represents the total number of individuals that a particular system can support. So if you had a system that would support 1,500 individuals, and you have very few, like only 1 or 2, 1,500 minus 1 or 2 would give you a number up here that's very, very close to 1,500. 1,500 over 1,500 would be 1, right? So this term would be very close to 1. That means you'd basically be growing to something very close to the maximum rate of increase, or the exponential growth rate for that particular species. If n starts to get very close to k, so if this was like 1,500 and this is like 1,498 or something, then this term starts to become close to 0, which means that basically your rate of increase would be close to 0 and the line would start to level off. This shows it to you in a table. This says, you know, carrying capacity is 1,500, right? If you look at the population size is small, then that means this term of k minus n over k is very close to 1, which means that you're very close to the maximum rate of increase. If you're at 1,500, right, then this term is 0, which means that you're not growing at all anymore. And if you graph that, you end up with something that looks kind of like this. You'll notice the first part of this graph is just really an exponential curve, right? when this term is very close to 1, you're growing exponentially. It's only when this term starts to approach 0 that it begins to level off. Yeah. And of course, you could end up with a situation where n exceeded k. What would that do? If you had 2,000 individuals and the carrying capacity is only 1,500, that's not good. Yeah, that means this is going to be a negative number, and that means you're going to be decreasing in population size, right? So this just compares an exponential growth curve to a logistic growth curve. And then this shows you 2 growth curves taken from real data. So here's some paramecia in a lab, and you can see this looks very much like that logistic growth curve that we just saw, right? So when you have very few individuals, they are growing quickly, right? The population is expanding almost at biotic potential. And the closer they get to the carrying capacity of the system, they kind of level off. How about those little Daphnia there? What happened to them? I mean, the growth curve should go something like this, and what's this over here? You kind of saw this in the lab, didn't you? What happened there? They overshot the carrying capacity of the system. Dramatically, they overshot the carrying capacity of the system. You can imagine we started here with like, what, 5 little Daphnia? And they're in there in a system that's capable of supporting about 130 individuals, right? That's where the carrying capacity is. So those 5 are in there going, woohoo, let's have a party, right? And they're all having babies like crazy and everything, and they're growing so quickly in a very rapidly expanding population. These little guys are not going to know where this line is. They don't know what the exact carrying capacity of the system is. So it's very common for them to overshoot it. And then when we're up to 190 individuals and the system only supports, it only has enough food and resources for 130. Nature doesn't allow that to exist very long, right? So it immediately corrects and brings it back down to whatever the carrying capacity is. It's very common for rapidly expanding populations to overshoot carrying capacity and you have to correct. And it's kind of painful, right? Because like about 1/3 of them had to die in order for this to get fixed. The question is, like for us, if humans are in an exponential growth phase right now, where is our carrying capacity? Most people don't have any kind of an idea at all. Have you ever heard somebody suggest what the carrying capacity for humans is on Earth? Probably depends on how well you want to live, right? I mean, if you're willing to live like in a little box and eat like rice every day or something, you can probably support a lot more people, but it becomes sort of a question. I mean, obviously a Daphnia doesn't really care how it's treated as long as it has enough food to survive and live at all. It's going to be probably okay, I mean, it's going to survive how it can, but humans are different, right? We have certain quality of life expectations, and, that's going to come into play as to what the carrying capacity is. But I've never heard somebody suggest that the world can support 14 billion people, or, I mean, what is it? Isn't that where we are now? We're at 7 now, that would be doubling, not quite 14 yet. But, or 20 billion, or 25 billion, I don't know. Have you ever heard an estimate of what the carrying capacity for humans on Earth is? I don't really know. I think a lot of people think we're past it already. Okay, so how about this? Exponential population growth is not possible in natural populations, it's not relevant to logistic population growth models, it's not sustainable in closed systems, or all of those. Anybody else? Joel, he's not there. He's looking outward.
Yeah, my number just broke.
You're the only person whose number I actually know.
I can do it on a piece of paper.
That's okay.
I won't erase it when I see the right answer.
That's okay. Okay, let's end it.
No.
How many more questions are there gonna be?
There's 2 more sets of PowerPoint slides after this. I don't know, there's probably like, how many are in each one?
Yeah, it's right underneath in the upper right hand corner.
Not too many more.
Wonder if I should go buy another clicker.
Well, I mean, 8 to 10 would translate into what, about 4 points or something?
I'm not gonna worry about it.
If you got them all right. Okay, is that it, 15? I thought somebody went, no. But okay, let's try 15. It's not sustainable in a closed system, right? But first part of a logistic population growth model is an exponential curve, right? Right? So it is relevant to it. And of course, it is possible in natural populations. I just showed you humans and elephants and stuff like that. It's just not possible for a long period of time, right? Okay, populations are most likely to exceed carrying capacity, like those little Daphnia did, when they have persisted in a stable environment for considerable time, when they are growing rapidly, when a predator is introduced to the system, or none of those. When would a population be most likely to exceed carrying capacity? You only have 2 more lectures with all these crazy questions that come up there. And you'll go to some other instructor who will write crazy questions, different crazy questions. Now, some of these questions I look at myself and I can't really understand them, and I wrote them. Okay, 2 more?
Hold on.
There we go. Okay.
Yes.
All right, okay, I'll get it right, so. Okay, and then this is out of Campbell. So this shows you the age structure in different populations, and it basically, from this, you can tell whether or not a population is growing. So this is a little outdated, I'm sure, but this is supposedly the age structure in Afghanistan. So if you'll notice, I mean, like, these are people that are 0 to 4 years old, all the way up to people that are over 85. And if you look at this, you can tell in Afghanistan, there's just like a lot of young people, and not very many old people, right? So this type of an age structure indicates that you've got rapid population growth. You've got a lot of birth at the bottom, and not as much death at the top. So basically, you're very bottom heavy. If you look at the United States, it's kind of like this, except it's not as dramatic, right? It's still bottom heavy. You still got more people that are young than you have people that are old. So it indicates that you're growing, but you're growing more slowly. And if you look at something like Italy, supposedly, the largest, or the age classes, or the greatest number of people are in sort of middle-aged age classes. So it kind of indicates that the birth rate and the death rate are more or less the same, which that would indicate that you've got no growth. You could imagine one, they don't show one, but that's kind of upside down, right, where you had sort of a very small, younger class, right, and you had more people that were of older age. That would imply that your population was doing well. Actually, probably declining, because you don't have enough births coming in at the bottom to support the people that, or to replace the people that you're going to be losing at the top. Yeah.
And what year was this?
I don't know, whenever Campbell was 2008, or it's 8th edition, so I don't know when that came out, wasn't it? About 2008, I think,
Yeah.
when they replaced that.
A year or two ago or something like that.
Yeah, I don't know. But I don't know how updated this was.
Some problem with it?
published.
Oh.
Okay, so we talked then about this idea of carrying capacity, or K, this set of environmental factors that limits a population so that a population doesn't grow indefinitely at its biotic potential. And so now the question would be, what types of things contribute to K? And we refer to these as limiting factors. Hopefully you realize carrying capacity, when we were doing the lab, we were kind of calling it the steady state or the equilibrium value. Those are all the same thing, right? It's basically what is the population size for a particular population that the environment can support. And it's determined by limiting factors in the system. Typically, these limiting factors are categorized as being density dependent and density independent, so that's the way I'm going to try to do it. Some of these are sort of more straightforward than others, and I kind of even messed myself up on this one when I was talking about it yesterday. So let's see if I can do it now without messing myself up. So food and water, right? Density dependent means that if there's more individuals in the population, this limiting factor is going to be more important than if there's fewer individuals in the population. So that kind of stands to reason, right? If you're those little Daphne and stuff, if there are a lot of you, food is going to be a much more critical limiting resource than if there's very few of you, right? So if there's 5 Daphne, they've got food galore, right? If you've got 120 or something, you're getting really close to carrying capacity, there's going to be a lot less food because there's a lot more individuals. So it's a density dependent factor. It's a critical factor if there's a lot of individuals, not so critical if there's fewer. Water availability could be the same type of thing. Space, obviously, is a bigger deal if there's more of you than if there's fewer of you. Light, if you're a plant, and you have other plants that are crowding out the light because they're covering you over, that's going to be a bigger deal than if there's very few plants and they're sparsely distributed such that they're all able to be in the light, right? Fewer plants, not as much crowding, more light for everybody, so it's density dependent. You can imagine if you're in an aquatic system, oxygen, carbon dioxide, or nutrients, if you have 10 goldfish in a little bowl, oxygen is going to be a much bigger problem for them than if there's only one, right? That's why you don't want to have, that's one of the reasons you don't want to have too many fish in too small a bowl, because they'll deplete oxygen out of the system. Mate availability, everybody has to find a mate, right? But if there's a large population, you're going to have much greater competition in trying to find a mate. If there's only a few individuals that you could potentially mate with, and you have a lot of competing males, for example, that are all trying to get the same female, that means finding a mate is going to be more difficult than it would be if there were fewer males. A lot of animals, too, have territoriality. They actually need to find a mate and then stake out a territory. This, of course, kind of goes right along with space, right? But you need to have enough area so that you can actually set up a family and mate. For example, you can't take like 20 lions and put them into an area as big as this room and expect them all to just live in peace and find a way to have babies or something. They're just going to fight like crazy, right? It's too small an area for them to really be able to stake out what they need to have to be able to mate and produce offspring. Disease, how about that one? That one always kind of hits me a little weird because it seems like it should be density independent, right? Density independent is going to be some kind of a factor that's going to set K in such a way that it doesn't really matter how many individuals are in the population. Anybody know why would disease be a bigger problem if there's a lot of you than if there's just a few of you? It seems like if the disease comes in and just kind of like it's wiping you out, I mean, what difference does it make if you've got a small population or a large population? You know? It has to do with transmission or communicability of a disease. So if you have a lot of individuals packed tightly together, a disease tends to spread through the population more quickly. You'll see when we get to density-independent limiting factors, they talk about toxins. So toxins, because they're not really spread by individuals one to the next, are considered density-independent. But disease, if it's communicable, if it was some kind of a disease that wasn't communicable, it probably really belongs with density-independent. But if it's communicable, you could imagine it being dependent. More individuals in the population are going to make it more of a problem. How about increased predation? What that means? So why would you be likely to be more preyed upon if there were a lot of you than if there are just a few of you? You know, that again seems to me initially like it should be density independent. Sort of like,
Scarcity of food.
Okay, you're on the right track. Scarcity of food maybe for the predator. So it ends up that if a predator has a whole bunch of a particular prey that it can specialize on, that it will do that, right? So if there's like 5 little rabbits out here, there's just like not enough of you for a predator to really care, but if there's 500 rabbits, all of a sudden the predator's going to go, wow, I better eat rabbits. And he's going to start getting very specialized on that, so it dramatically increases the predation. So increased predation is going to be much more of a limiting factor if there's a lot of you, because it allows for the predator to specialize on you as a food source, rather than if there's very few of you, the predator's probably going to kind of ignore you because you're just not plentiful enough to actually be a good food source for that predator. Does that kind of make sense? So that's what makes it density dependent. You're more likely to have increased predation if your population is large rather than if it's small. I'm not sure that would have occurred to me, but that's the way that it's thought of here. Increased waste production, that's the other reason you don't want 10 goldfish in a bowl this big, right? Because not only are they depleting oxygen more quickly, but they're also producing more waste. And then there's even this thing called intrinsic reproductive control. So for example, if you're in a population that's large individuals tend to have fewer babies than if the population is small, and you can see patterns like this. I'll show it to you in a graph on the next slide here. I wanted to come back to, remember when we talked about this idea of R selection versus K selection? Yeah? Y'all know what the R stands for, right? What does R stand for? It's like the R, which is little b minus little d, right? It's basically the rate of increase. You can almost think of it as the intrinsic rate of increase, right? Basically, how fast could a population grow without any carrying capacity limitations? K, of course, refers to carrying capacity, right? If you talk about have you all heard these terms before? I asked them this in the other class. Probably at some point you guys are thinking you're taking MCAT or PCAT, or at least a lot of you are, some kind of a standardized test. These are the types of things I think if they were going to ask you Bio 2 type stuff. Some people have told me, oh, I just took the PCAT and there were a bunch of Planck questions. I'm like, really? People have told me that before. But usually what they come back and say that there are is they usually want you to know something about ecology. And this would be the type of thing that they'd ask you, because this is sort of a very basic idea in ecology. And a lot of people say Hardy-Weinberg, the other thing that they, because it's the way that you would, for example, if you had an infectious disease or something, it's the way that you would track it would be by using some kind of a population genetic approach. So that often shows up there. At any rate, I thought maybe some of you had heard this. Maybe even if you didn't know what it meant, you'd at least heard it. If we say a species is R-selected, what that means is that it has reproductive traits that are designed to just crank out babies like mad, right? So if you're in a population where the population size is way below the carrying capacity, you can expand that population very, very fast because you have a lot of kids. Your kids are crummy, but if you're in a system where there's no competition and almost unlimited resources, your crummy kids can survive, right? A K-selected species is a species that it has a reproductive strategy where it puts a lot of energy and a lot of resources into each one of the offspring. So you have very few offspring, but those offspring are very strong in the sense that they're competitive. So if you're in a population where you're very close to carrying capacity, right? We can only support 1,500 individuals and they're already at like 1,490. You're going to want to have just a few kids who are going to be really good at competing so that they're able to outcompete everybody else's kids and stay in the pool here. Otherwise, they're going to get knocked out, right? So an R-selected species would be something like, I don't know, a seahorse or something, right? Where the seahorses have 10,000 babies and one of those 10,000 actually makes it, if you're in a system that's close to carrying capacity, right? Tons of kids, very few resources into any of the kids. So most of the kids die, but a couple make it to the top, right? This type of a species is very, very good at expanding a population very quickly. A K-selected species would be something like us, right? People cannot crank out babies really, really fast, but when they do crank out babies, the babies are of pretty high quality, such that they're very competitive in a system that's close to carrying capacity. I've asked this as an extra credit question before. I've asked, like, what is R selection? What is K selection? What does the R stand for? What does the K stand for? Give examples of, you know, one type of R-selected species, one type of a K-selected species.
So like fish be like ants, because they produce so many eggs?
It would depend on, typically something that has a large number of offspring, but with very little parental care, very little resources. So a lot of fish would fall into that category, right? Anything that has a really large number of eggs, something that's having only one or two offspring at a time and really spending a lot of time on them, and a lot of energy, is going to be something that's more K-selected. And obviously, if you ask me which strategy is better, well, I can think of zillions of species that do this, and I can think of zillions of species that do this. So it really depends on the particular niche that little species is filling as to what type of reproductive strategy. And obviously, this is a little bit, you know, artificial, right? There are some species that are sort of intermediate, probably, and not extreme R-selected or K-selected species. But a lot of species you can put in pretty much categories being more one of these than the other. Yeah. Okay, so this shows you a density-dependent limiting factor. That idea of intrinsic reproductive rate is decreased. So here it has like these little sheep or whatever, and you'll notice that this tells you how many of the pairs of sheep are producing lambs or having babies. And this tells you the population size, and you can see that it decreases. So if you're in this population and there's more of you, fewer individuals are having babies. It's just sort of an intrinsic reproductive control. Sort of like you're not going to be everybody having lots of babies if the population size is bigger rather than if it's smaller, so that's density dependent. This is supposed to be showing what? little cheetah doing there? He's marking his spot. So this is like territoriality, right? That each one needs to have its space and find a mate, and that's going to be a bigger factor if the population is large rather than if it's small. And this is kind of showing the same thing, right? This idea of space or territoriality in these little birds, right? That each one needs a little spot for its nest. Okay, and density independent factors would be things like temperature, you know, and you might make some kind of odd arguments as to how some of these could be density dependent, but typically if you need a particular temperature in order to be able to function and that temperature is too low or too high, it's probably going to depress the size of your population, and it's not going to do it in a different way if there's a lot of you versus a few of you. I guess if you are able to rely on other individuals for body warmth or something like that, you could somehow argue that it's density dependent, but under most circumstances, temperature would probably be independent of the number of individuals that are in the population. Likewise, precipitation. Now, if you're just talking available water, remember water was actually under density dependent, but precipitation would be sort of more like overall annual precipitation, and that, if that's limiting to your population, if it's a limiting factor, is probably going to be limiting independent of population size. Toxin, again, I said it's kind of different from a disease because it's not communicable, it's not being passed by individuals, so it shouldn't really limit based on the density of the population. Salinity is kind of like temperature, right, or something like that. It has to do with sort of ambient conditions that could potentially depress your population growth, but probably not tied to the density of the population. And altitude and atmospheric pressure would be sort of the same thing, right? There's sort of external environmental factors that are really not going to be more or less critical based on the number of individuals that are in the population. And so this idea that populations are dynamic, they're always changing. Natural populations fluctuate in size. Sometimes they follow somewhat predictable patterns, but other times they're a little bit less predictable. Y'all did this, right? This shows lockable Terra predator-prey cycles. Have you heard of lockable Terra before? I mentioned, like in the lab, that lockable Terra sort of is to ecology models what Hardy-Weinberg is to population genetics models. So these are really, if you were to look at the vast majority of ecology models, they all sort of start with a lockable Terra model. And basically what it does is it models the interaction between two species in an ecosystem at its simplest. And then you can make it more and more complex, but that's what you're doing at sort of its very simplest level. And the little equations are actually in the lab manual. I put them in there. So a lockable Terra predator-prey cycle shows the interaction between a predator and a prey. If you have a system where really the primary control on the predator is a bottom-up control by the availability of prey, and the primary control on the prey is the top-down control of the predator itself, then the two populations are just controlling each other. And so if you think about it that way, there really is no other control in the system, which is not very realistic. But in some systems, they almost behave as though they were. This is like real data coming out of the number of wolves and the number of moose, right, across in this particular area across these years here. And you can see that what happens is you have a moose population. So let's imagine there's 3 moose out here and they're running around. There's a little wolf over there. And then the moose are going, wow, you know, got all this great land out here. And so they start having baby moose, and right, and all of a sudden you got a big herd of moose. And then the wolf's going, wow, look at all those moose over there. That looks great. So I guess I can have babies and start raising kids and have a big family because I got all this food running around on the hoof out there, right? So then they're hunting all these moose, and eventually you start to get this really large number of wolves, and then the wolves start eating more and more of the moose and start sort of driving the moose population down, right? And if they get it too low, then all these wolves are going to realize, wow, we don't have any food anymore, and so then the wolf population is going to start to decrease. The wolf population starts to decrease, that's good for the moose, so the moose start to increase, and they basically just cycle like that. But you'll notice that the moose always precede the wolves. Whatever the moose do, if the moose go up, then the wolves go up. If the moose go down, then the wolves go down, right? They're always following, the predator is always following the prey, which is kind of intuitive actually, because the predator does follow the prey, right, when you're in the chase. So this shows it with a lynx and a shoe hare, and you'll notice it just cycles like this. You don't ever really reach steady state values. The reason you came with steady state values when you did the extend models is because you had multiple bottom-up and top-down controls such that you end up establishing these steady state values. But in this, you just have 2 populations and each one is the control of the other. And so what it does is it just endlessly cycles like this. Lockable Terra, it doesn't just have to, model predator and prey, it could also model two that are in competition. If you think about it, the predator and the prey, in a sense, are in competition with one another, right? The prey wants to escape and the predator wants to catch the prey. So they're kind of competing to see who's going to get to win, right? Either escape and live or eat and live, right? So they're in competition in essence, and so you can use this exact same model, almost identically to what you do for predator and prey. You just insert two competitors, right? So Lock and Volterra is used very often to show to model competition. Any type of community interaction you can model with a Lock and Volterra model. Okay, and then the last part of this is this idea of a metapopulation. So a metapopulation is a population that's highly subdivided. So when you have little islands of suitable habitat and they're sprinkled across a large area, you have these small subpopulations that regularly go extinct and then are recolonized so that they come back again. And this shows some little island off of the coast of Sweden, I guess, right, that has this little butterfly. You can see all the little black dots are little local populations where it exists. All the little white dots are places where it did exist, but it's not present right now. And you can imagine going back in a year, you'd look at all these little dots again, if you're really determined to do this. That looks like a lot of work to me. And you try to trap the butterfly, and probably a lot of little white dots would go black, and a lot of little black dots would go white, right? Just because it's not going to be everywhere that it could be all the time. And these are very interesting systems to look at sort of like patterns of local adaptation and diversification, and also this idea of migration and reestablishment and barriers to that. I looked at this to a certain extent when I was looking at my mushroom and Hawaiian Islands, because it's spread across the entire archipelago from Hawaii down to the Big Island, but it only lives with native Hawaiian plants. And so in these little pockets of native forest. So I had something you might almost argue would be like a metapopulation in my study, but a lot simpler metapopulation than that one. Okay, and then the very last thing in here has to do with this idea of life expectancy. So what's the life expectancy in the U.S., do you know? No, it's not 90, like 70 something maybe.
Yeah,
Is it up to 80? It's a little bit higher for women than it is for men. And it goes up a little bit, right? We have pretty good medical care. And yet if somebody asks you, like, what was the life expectancy like in the old Wild West? Wasn't too good. I think it was like 40 or something like that. And even if you go back to like colonial times, it was like 35 or something, you think, oh wow, you got all those poor people running around like in colonial Pennsylvania that keeled over when they were 35. And yet you realize that's not really right, because you can probably think back and go, well gee, I can remember some people that kind of got old, right? It seemed like there were a fair number of old people. And so the reason that you kind of get lost in this a little bit, notice industrialized countries tend to have higher life expectancies than less industrialized countries. But if you look here at this thing, infant mortality, right, you'll notice industrialized countries have much less infant mortality. So the way that they calculate life expectancy is basically they just take the age that everybody dies at and they average it together. Did you all realize that? In other words, it's not really, even though we say life expectancy, it's not really how long we expect you to live. It's really the average age at which people die, yeah? So for example, if you had like somebody lived to 70 and somebody lived to 69 and somebody else lived to 85 and somebody lived to 70 and somebody lived to 65 or something like that, but then you had 5 babies that all died as infants, right? Here's a bunch of zeros. So when you average that, what do you end up with? Like 35 or something. So you go, the life expectancy is 35. It doesn't mean you're going to keel over when you're 35. It means that we've got a lot of infant mortality. So you've got to be a little careful with that. Very often when they say that a country has sort of a very low life expectancy, it's really not that people are dying at 40 or 50. It's that you have very high infant mortality rates. And when you average in all these zeros, right, it ends up giving you a very low life expectancy, even though people that reach adulthood tend to live sort of what we would consider to be a normal, to a normal age. Yeah. Okay, so the R in R selection refers to carrying capacity, intrinsic rate of increase, population size, or the strength of selection. If I were writing this game, I read a question like that. Did we have 15? Pick an answer. Okay, I'm gonna end it. Where's the other? Okay, I'm gonna end it. Everybody have their number up there? Okay, I think there's another one after this. Good, most of you got that right. Population size would be represented by an N typically, carrying capacity by K. Strength of selection is not really in this at all, right? This doesn't have anything to do with strength of selection, it has to do with mode of selection that favors like large numbers of offspring that are not well cared for. Okay, and the lockable terra model can be used to model competitive interactions, can be used to model predator-prey interactions, illustrates fluctuations in population sizes attributable to community-level interactions, or all of this.
Have you ever done a multiple choice like test?
No.
No.
You mean that I wrote?
Yeah.
With my high school kids.
That's it.
Yeah. I don't like them very much. Can you tell?
Maybe a little bit.
Okay, is that it? Are we done? We're down to just 14. Okay, good. All of us, right? Okay, so here's the good news. There's only 2 more PowerPoints left. Oh my God. The bad news is I've only got like 35 minutes right now and 1 more lecture. We gotta go fast.